So, as we were discussing in the previous segment, we are going to take up the case where we have three fluids in a way. I'll draw it. Yeah. And this is some fluid. I'll call this a fluid 1, fluid 2 and fluid 3, is it? Yeah. Okay. And they are characterized by rho 1 C1, rho 2 C2 and rho 3 C3. And in the last segment we wrote also the equations. Okay. Now equations of the what do I call the pressure waves which are say coming and pressure waves which are say reflecting back. So this is in region 1, say P2, P2 and then say 3. So that's how we this was the setup. Okay. So then what we will do is I told you also in the previous segment that we will try to evaluate the unknowns which are there in these expressions of pressure fields, because we said that the steady state has been achieved, and once the steady state has been achieved, there will be some phase and there will be some magnitude ratios. Okay. Now, so those are our unknowns in these pressure ones. Okay. So those things which are unknowns, we are trying to evaluate them, and then how we will do that? By writing boundary conditions. Okay. Wherever we know things, relationships between them, we will write them and figure out those values. Now, if you remember the expressions which we wrote last time, we took the x coordinate. I'll do one thing. I'll move this a bit here so that, yeah. Now, so this is our x direction, and because the length of this middle section we took as L, so at this location x was L. So here, if you remember, the kx term started with kx minus L. Okay, done. So that's just a recap. Then let's say we will write the first equation of pressure balance at this location at x is equal to 0. So from that you also try to write along with me, so that you will get what I am doing. Okay. Now okay, because this is an independent section, I will say I'll write in detail, but you use your notes so that you can get the pressure equations directly. Okay. At x is equal to 0, now Pi plus PR in region 1 is equal to Pi plus PR in region 2. Okay. So that's the condition which we will impose at x is equal to 0, and that will give you let me write it, otherwise is a a1 e raised to j omega t minus k1 x. Okay, and so if you put x is equal to 0, so you will get similar things here, when only e raised to j omega t will be there. I'll just write one more thing for the end, then I'll not write any other. Pt of say 3 will be something like a3 we used, right? Yeah, a3 e raised to j omega t minus k3 x minus L. So that's other things you should be able to write. Yeah, now using this, then we can write what we can write is a1 plus b1, okay, is a2 plus b2. So here I can write that, okay, this will have a1 as an unknown, this will have b1 which is a complex as an unknown, this is a2 complex, b2 complex, a3 complex. So these are the unknowns. Okay. Now, so this is your first equation which you will get. It's fine. Then, so this I can write as equation 1. Next, if you try to balance the or continuity of the particle velocity, you can write the other equation. I used 5th page to start with. Okay. Then a1 over rho 1 c1. So this is like, you know, u1 amplitude from u1. I'll not say this is u1. This is from u1. Okay, which is complex because we are writing the velocity amplitude plus b1 amplitude over rho 1 c1, but with a minus sign here. Okay, that you should be now comfortable with why this minus is coming. So that will be equal to a2 complex over rho 2 c2 plus b2 over rho 2 c2 with a minus sign here. Okay, and this comes from u, this is ui, I'll say u incident, this is u reflected in 1, this is 1, and this is from u incident of 2, this is from u reflected of 2. Okay, yeah, so that's what we are summing up and then cancelling out the e raised to j omega t term, yeah, at x is equal to 0. So these are also at x is equal to 0 for any time to come. That's why they are the boundary conditions. So that I will call as, say, equation 2. Similarly, equation 3 will come from the pressure balance at x is equal to L. Okay, so at x is equal to L, again the pressure balance will give you, I'm just writing the final equation, you use the equations of pressure field to write it, e raised to minus j k2 L, okay, plus b2 e raised to j k2 L. So just for this equation I'll tell you. So here in place of this x you just have substituted L, nothing else. Okay, so a1 e raised to j k1 L. So this is that term. K2 should be k1. Oh, we are writing at k3, right? I mean, that's fine. You, sorry. we are writing at x is equal to L, so that's why in not this equation, basically we are using K2 thing, okay, Pi2. So this equation at L we are putting it, okay. Yeah. So that will be equal to A3, and then what would be this term which will come here, next term? Nothing else, because that is where if you put x is equal to L there, so this term just goes out, you are remaining with only A3 e raised to j omega t, which gets cancelled. Okay, so this is your equation 3. So this is pressure balance, and at x is equal to L, velocity continuity will give you an equation rho 3 C3 after the cross multiplication, okay, after the simplification, A2 e raised to minus j K2L minus, this minus is coming again every time you think about this minus, okay, why is it coming? B2 e raised to j K2L is equal to rho 2 C2 A3. So this is your fourth equation. Fine. Now, and then please note that all these equations are complex equations, okay, they involve complex numbers, okay. And so then from 1 and 2, now we are in a position to solve them. The thing is, where is 1? Oh, okay, this is 1, this is 2. So from 1 and 2, if you eliminate, means try to evaluate A1 in terms of A2 and B2. So that if you do, you will get this equation. So rho 1 C1, so you can do the algebra later, rho 2 C2, this is simple, add 1 and 2 and done. A2 plus rho 2 C2 minus rho 1 C1 B2 over 2 rho 2 C2. Okay. Now A1 in terms of A2 and B2 you have got, and then from 3 and 4 what you should do is you get A2 and B2, this is B2. Okay, get A2 and B2 in terms of A3. Okay, get A2 and B2 separately in terms of A3 and substitute that here. So that final equation you will get is A1 in terms of A3. Okay, so the intermediate things we are just getting rid of. So I'll write the final expression. So A1, where is that? Yeah, is equal to rho 2 C2 rho 1 C1. I will write even the next level of equation, skipping one more step. You can always see that in the notes. Yeah. Rho 3 C3 plus rho 1 C1 divide by 2 rho 3 C3 cosine of K2L plus, so this is the real part, plus j times rho 2 C2 squares plus rho 3 C3 rho 1 C1 divided by 2 rho 3 C3 rho 1 C1 sine of K2L. This is the final expression which you will get, okay, after doing everything. Fine. something I am missing. So this is A3. Okay, because I said that A1 in terms of A3 you will get. So this is the ratio of A1 to A3. Because e raised to jkl, e raised to minus jkl you will get, and then just split them up, expand them, and you will get it. Okay, and then if you want to calculate that, because this is what is important to us, that the transmission coefficient. If you have a in between layer of fluid, so how much energy is getting transmitted. So that's the motivation with which we did this. So you will get this as, and then this is what energy transmitted by energy incident. Okay, power transmission coefficient. This will be now your PT, amplitude in third domain square, over 2 rho 3 C3 by P incident in 1 squared over 2 rho 1 C1. Okay, so that's what you will get, which is nothing but rho 1 C1 by rho 3 C3 times A3 over A1 mod square. So from here you can simply calculate its amplitude by this square plus this square, you will get it. Okay, because it's the complex form, and that's what you, so substitute this term there, so get the alpha, and so this is called the coefficient. Okay, so sound power transmission coefficient. Then there is another term which is generally used, is sound power transmission loss. Okay, so this is coefficient and this is loss. Loss is generally expressed in terms of dB value. So always you in literature you will see this many dB is the reduction, not as a number, because this will be some 0.0012 like that. So they don't express like that. So this is nothing but 10 log of I incident over IT, or you can say 10 log of 1 over alpha t. Okay. So in dB you can express like this. Okay. So let's so what you do, I'll stop here. Let's take, just to get an idea of the values what you are getting. Let's say rho 1 C1 is say 415 air. This also is say 415. Why? Let's say some other number. Say 600, and this is say 2000. So so please calculate how much dB of reduction or transmission loss you will have. Okay. So that you do. I am stopping this video here.